Recording, that's fine. Okay, this is what we talk about on Monday. So the layout style. And today and next Monday, we will be very focused on how to do the layout efficiently and make sure that you don't make any mistake when you lay out your circuits. So remember that we said when you are forced to design a very wide or fat transistor, the best strategy is to use the finger style. That is, you divide the W, big W, into two halves. Okay, W over 2. Okay, and the current comes from the both sides. Okay, and they meet each other in the middle and get out from here. Okay, the drain and the source. Well, of course, if this is a PMOS, the direction of the current will be reversed. So this is very wide finger style. And before I close the session on Monday, I also mentioned this stupid layout. Don't ever do that. Okay, from time to time, you might need something like this. You might need something like this. Okay, you might need something like this. You're going to have a resistor over here, resistor load, something like this. And this is a source, this is a drain, this is a source, this is your gate. Okay, and for those beginners, they say, oh, okay, why don't we just directly take the advantage of the diffusion? Because diffusion is a high impedance device. So automatically that we can assume it can be used as the inverter. But the thing is, if this resistor is made of diffusion, okay, just like on over there, can it be a resistor? The answer is yes. But if you ask the next question, can it be a reliable or predictable resistor? The answer is no. Okay, there are two major ways to implement a resistor on silicon. The other one is polysilicon. The other one is a polysilicon. Okay, so this is your schematic, but the step after the schematic is that you have to lay out your circuits. So don't you do that, because the diffusion, the accuracy of the resistance is around 30%. That means, okay, this resistance is highly dependent on the voltage on both sides and the temperature of this material. And that is why it would not be reliable or accurate. But instead, if you are going to use the other material, which is very much appreciated, is a polysilicon. We'll talk about it more. And this one, if this process is provided by TSMC or UMC, the accuracy could be as good as 0.3% to 1%. That means it has a very high isolation or resistance to the temperature variation or the voltage. Okay, so in your electronics study, you always assume this is an ideal resistor. But when it is implemented with real material, the materials, no matter which one you use, okay, both of them will be affected by two major factors. Okay, the first one is temperature. That means the resistance of the resistance of this material will be affected. Number one is resistance. The second one is the voltage drop on both sides. Voltage drops. Okay, believe it or not, this is a resistor. In the textbook, it is ideal. It will not be changed, okay, no matter what happens. But the thing is, you're going to learn something that when the voltage here, V1 to V2, there's a delta V over this two. And the resistance of this resistor will be affected by the delta V. So I call this is a second factor to affect the resistance. So I'm telling you that if you need a resistor, okay, you are going to use this one, polysilicon, okay, don't ever try to use that one, diffusion. This is a bad idea. Because parasitic resistance and capacitance, okay, is so bad, maybe you can hand estimate it by counting the square and unit length of their parameters respectively. But the thing is, the resistance that you expect or you like, okay, when you are doing your pre-layout simulation might not be the same as the one that you lay out, okay, and you get it from layout. That's highly impossible. So this is important one, okay. This is a lousy example, and do not use this design in your circuits, okay. And the counterpart of a white transistor is that, what if you are going to have a very thin or very long transistor? Okay, so we have a basic idea. When we have a big fat or white transistor, okay, you are going to use the finger style, okay, and then what you do is divide it into two parts. Okay, something in the middle. This is your source. Okay, and you have poly over here. This is poly, and this is poly. And this is a source. Both sides are a drain. So this is what we draw before, and the current comes over here. Okay, then you have a very big white. This is W, this is W. Then you have two W's, then you are going to realize a big fat white transistor. And the counterpart is this one. Okay, what if you have a thin and long transistor? Okay, this is big W. And this was a big L. Big L. From to time, you might need that, big L. Very long. This is the way you can learn. All right? So here we go. And this is a polysilicon. Okay? And this is a drain, this is a source. All right? If we have a high voltage here, let's assume this is an N transistor. Then the voltage is high. Then the high voltage is going to drive, okay, this gate. And the current, how the current travels, okay? It will start from the drain and go all through these high and lows and go to the source. So the distance, okay, you have to count, is from this point to over here. So it's going to be a long one. Is that understood? Okay, and this style is called snake or serpentine. Some people call it as a snake or serpentine. You got to use this way. Snake or serpentine. Okay, this is how you realize it. All right? This is the active area, and this is a gate drive. Okay, this is a very big L. When you need it, okay, you can directly mimic or copy it. This is a very good example for you to follow. And this is a big, even bigger, a big one. See that? Okay, you see how many fingers? 1, 2, 3, 4. Is that 4 fingers? See that? 4 fingers. This is even bigger, even bigger. So where is the gate? Gate's over here. So when the gate voltage is high, so the transistor here is on. It's on. It's on. It's on. Okay, where is the drain? Drain is coming over here and this way. So the current will come from the top, split it into 2 parts, and when the current hit here, okay, the current, see that they have both sides, they will be split into 2 parts. So a total of 4 small currents will be divided by this style. So this is 1, this is 2, and 3, and 4. Okay, and these 4 currents will be collected into the middle source over here. over here. So this one is quite easy to be understood. It is a 4W over L. 4W over L. Okay, this is very wide. So by the similar methodology, if you need 8W, 16W, you can do it the same way. Okay, it's a finger style. It's a finger style. All right, so this is a way that you should learn. So as I said, I will be, I'll give you more examples about how to do the efficient layout. So this is a finger style. Okay, and this is another way to realize two transistors in series with different what? With different lengths. See? We have a common gate over here, and it's going to be used to drive number 1 and the number 2. And the current goes from the left to the right. Okay, so the traveling distance is this way. So the current will pass this distance and the next distance over here. It's L1 and L2. So this will be equal to W, because the width is the same, W over L1 and W over L2. That means you have two transistors in series. Okay? This is one of the ways that you can learn. So we have the same width, but different lengths, okay, in two different transistors, MOSFET. So this is a way that you can learn. And there are more examples. Now this is the most fundamental layout for an inverter. All right, okay? So what is the difference between the left and right? So I'm going to erase off this one. So every logic gate in digital design starts from an inverter. So you learn this is simple when you are undergraduate, when you are first year's freshman, you know this one. Then in your second year, you know that the inverter is composed of one P transistor and one N transistor. This way, okay? So this is the way. Right now, this is for your sophomore year. Right now, you are junior students or senior students. That is a layout of this one. The layout of this one. Okay, so that's the layout of an inverter. So what is the difference of these two? See, let me tell you how to do that. How to, realize what the layout is. First thing first. So we have a poly over here. And that is this signal. So this is poly. So this is a poly over there to drive the gate. Gate 1 and gate 2. The gate of PMOS, gate of NMOS over here. And, excuse me, this is the area of the diffusion, N diffusion. That's the area of P diffusion. And they in the virtuoso, they are using the same color, okay, same pattern. Well, how to make make a difference? How to make a differentiation? This diffusion is sitting in the N well, so that software understands this is a PMOS transistor, this is an NMOS transistor. So this is a common gate over here, and this is output Y. Okay, and these are the V hole, okay, connect to each other and use the metal 1. So you understand that this is A, and this is Y, and this is metal 1. And then you have a diffusion for this part, and you have a diffusion for this part. But diffusion, this one, both of them are diffusion. How to make a differentiation? We got to let this diffusion sitting in the N well. Is that clear? All right, so this is how you do the layout. So this is how you learn. Right now you're a schematic designer, then you become a layout designer over there. Okay? Then the difference between the left and the right is that besides the connection to the ground and the VDD, in the layout, as we explained earlier, in order to prevent the latch-ups problem, so we got to add what? Well contact. Okay, it is called a substrate contact. So you got to punch a hole over here. This is V hole. And the purpose of this one is to make sure the bottom of this NMOS is shorted to the ground. Okay? In the same time, on the top, the well tab is to make sure that the N well, okay, the N well is coupled to, okay, the source of the P transistor. That is why. So this is not a complete layout, but this is the correct one. This is not so good one because it does not have well contact. So you have to add this one. Otherwise, you'll run into trouble. But the thing is, in the schematic, they'll never tell you, okay, they need a well contact. All right, this is an inverter. So this is a corrected version. This is not a complete version. Okay, now the next step, NAND gate. The NAND gate. As I said, everything in digital design starts from inverter. It's a NOT gate. So because we have an inverter, then we are going to evolve and develop two types. Okay? The NAND family and the NOR family. Okay? NAND family and NOR family. When we need a NAND, what we do? We cascade. Because as an inverse over here, we reverse it first. We have a series because it's N. We have a series in the bottom. Then because, as I said before, then if the two transistors here are in series, we are going to have a dual on the top. Okay, and this is signal A, B, A and B. Okay, this is for the NOR style. Okay, NOR style. And for the NAND style, sorry. And for the NOR, we are going to have two in parallel, okay, in the bottom. Then we're going to have a serial in the dual on the top. So this is A, B, A, and B. So these are the fundamental of two essential gates, NAND and NOR. So this is how it developed. Both of them are developed from the inverter. So for the NAND gate, you cascade, or you make a series of two transistors. For the NOR gate, you need two parallel transistors. And in the PMOS block, okay, you use the duality. So when they are in series, on the top they will be parallel. Okay, and it is the other way around. So this is for the schematic design. All right? So similarly, if we like to have 3 or 4 inputs of the gate of the symbol here, this is this one, and this is this one. This is one. The example on the screen is 3 inputs. So what we do, if we need more inputs over here, then what we do, we just extend it to C. It's the same. Okay? The more input you need, you're going to extend the N, and using duality, you're going to expand the PMOS on the top, okay, in parallel. So basically, that's how we do it. So, okay, so now you understand, this is a NAND type, this is NOR type. Now, since we are going to NAND example, I'm going to erase this one. And I'm going to tell you how to develop the layout of this one. All right, this is the NAND, 3 NAND transistor over there. So how do we develop the layout? It's quite easy. Okay, when you see a gate and then you want to do the layout, first of all, you use a dashed line, which is not a real line. Okay, you use a dashed line over here to divide it into part. This is for the N transistor, NMOS, this is PMOS. Okay, is that understood? So you do the N together and we do the P together, so no one will be messed up. Now you see 1, 2, 3. This is the output, so you understand very clearly. So what we need a layout. First of all, we have a ground. So apparently you need a metal line over here. This is M1, and this one goes to the ground, right? No problem at all, right? Okay? Then, since we have 1, 2, 3, we have 3 MOSes over here. Then we understand we are going to have a piece of diffusion. Right now, we don't care the size. We just make sure that you understand how to do it step by step. So we understand we need a piece of metal, which is going to be the ground. Then we are going to have a piece of diffusion. And then we need at least 3 poly, because we need 1, 2, 3 gates. So right now we need 3 gates over here. This is number 1, this is number 2, this is number 3. Right now we don't care the order. As long as we're 3, that's fine. All right? Then we have a piece of diffusion. We have 3 polysilicons over here. That means we have a 3 transistor over here. Now you check this figure. There are 2 ends. One of them shall be connected to what? To the ground. That is a metal over here. Is that correct? All right, so don't panic. So it's pretty sure that we are going to have this way, this one or this one coupled to the metal. All right, so don't worry about it. You can select which one you like. Usually, we place the output at the left-hand side. So if this is the case, it's pretty sure that we are going to have metal over here. This will be Y output. Usually, you say I'm a weirdo. I like to do the left. That's fine. Okay, but usually we place the output at the right-hand side so that everybody follows the same rule. So if we select this is the output point, output N, then the other one must go to the ground. Because this is output, this will be ground. So you are going to have a piece of metal over here. That is the ground. And check this out. This is metal, this is diffusion. So definitely you are going to have what? A contact. You got to dig a hole. Similarly over here, because these are 2 different materials, you got to dig a hole. Okay, you got to dig a hole and put a metal into it. Then what? Then there will be a short circuit. The signal can go through over here. So this is for what? For the NMOS. Is that all right? No problem at all, right? And then, similarly, after we finish the design, the layout of an NMOS, we are going to what? To take care of the upper part. All right, take care of the upper part. So definitely we are going to have a piece of metal, and this one is for the VDD. Is that cool? Right? That's fine. And then we are going to have, similarly, have a diffusion. All right? And then you will be confused. Well, how come we have 2 diffusions? This is for the N, this is for the P. Then you are going to use a big N well over here. If you close everybody, include everybody into the box, then the system will understand this piece of diffusion is for PMOS device, not for what? Not for the N device. So in order not to confuse you, so I'm going to erase the red box over here so you understand that this is what I'm talking about. Okay, anyway, you need a N well, right? So right now we use a symbol. This is N diffusion. This is a P diffusion. To stand for that, we already add a red box, okay, which is the N well, to make this diffusion as the PMOS device, right? So P diffusion is N diffusion. Okay, similarly, how many transistors we need? We need 1, 2, 3, right? So again, we are going to have 1, 2, 3. Is that clear? Right? 3 transistors. But the only difference of these 3 transistors from these 3 is that all of these 3 transistors, okay, both of their terminals, 2 terminals, as source and drain, one side must be coupled to power supply. The other side must be coupled to the output. So everyone is the same. You see? Power supply, VDD, output, VDD, output, VDD, output. Okay, how do we do that? Don't panic. Okay, you make sure everybody, okay, is at least one side is connected to the power supply. So definitely we need over here and puncture hole. That's for this one, right? That's for this one. Then, and the other end here, this one cannot go to the power supply because we are only allowed to have one end coupled to the power supply. So this one must go to what? Must go to the output. Is that clear? Right? Okay, then we check this one. Oh, all right, this guy, one side is already coupled to the power supply, output. The other side must be what? Go to the power supply, just like the one over here. All right? Okay. The last one, one of the 2 terminals is already coupled to the power supply, so the other one must be coupled to the output, just right over there. See? Then we make a terminal over here. And next step, because according to this schematic, their signals must be identical. So all we need is to make them short circuit together. Okay, and the layout is done. Is that clear? Okay, see that all you need, like this, and this one, the A signal goes to take charge of this pair of devices. B is charged over here, C is in charge of these 2, just like over here. So then you make a label. So this is A signal, this is B, and the C. Then you have your layout. And this is the first one. And now, this is not about the size, okay? It is about how to do it, logically, systematically, and efficiently. So this is why we have a similar layout over there. See that? And these guys make it smaller because they like to push it together. But you see that all the poly, they are shorted together. Okay, but the one I draw here is much more systematic. So you don't have to make a right turn or a left turn, and you have your layout. All right? Understood? So basically, horizontal N diffusion and P diffusion strips. Okay, this is the one I just draw. This is N diffusion, this is P diffusion. And the vertical direction is polysilicon. That is for the gates. And metal one, okay, for the VDD is placed on the top. And the metal one for the ground is placed at the bottom. All right? Then you can count how big the layout is. Because if you follow the rule of a design rule, you can estimate it how big this cell is, because you must satisfy the minimal width of this one, and that one, okay? And you don't have to remember all the numbers. All you need is to lay out it and activate the DRC, and the system will check that for you. All right, is that clear? Okay, sorry, before I go to the next slide, don't forget to add the well tab. Okay, otherwise it will violate certain design rules. So this is for the NAND gate. So what if I ask you to do the layout of the NOR gate right now? What if? Okay, I'll tell you the answer. The answer will be exactly look like this one, but the direction is reversed. If this is a NOR gate, okay, we are going to have a similar thing over here for the N devices, and we are going to have a series of pitch and sits on the top, look like this one. So for the design of NAND and the NOR, they are totally dual. So if you can draw one layout of one of the styles, then you can automatically know how to design the other type. All right? So this is the NAND 3. This is NAND 3. Okay, and this is not a layout. This is some old stuff. Oh, what do you mean old stuff? This is what I learned when I was young, 35 years ago. About 35 years ago, before you were born, we don't have that kind of luxury computers. We don't have too many workstations, and we did not even have sophisticated software. Before we go to the workstation to do the layout, we have handing a homework assignment like this one. It is called a stick diagram. Stick diagram, okay, in good old days, is a required step for students to hand in. And it used different colors to stand for the layout you will or you are supposed to do. For example, see, this is a blue. There is no thickness. Okay, just a straight, pure line segment. Okay, we use the blue pencils to draw the blue line segment to stands for the metal over there. All right, and the green stands for the N diffusion, and the yellow use for the P diffusion, and the big cross stands for contact, short circuit of different layers. All right, and red is a red line segment. It's a polysilicons. So this is called the stick diagrams. And right now, all the students, as far as I know, when I started teaching the VLSI, I never ever saw any student handling this kind of thing. Okay, every student directly go to the software, computers, or workstations to activate the software and start their drawing and playing this kind of thing. All right, and this is only good for your practice. You draw the color pencils or dry easy markers before you go to the computers, and this is how you do it. So just to let you know, you don't have to practice. Okay, now let's talk about how to do it efficiently. The one that I draw over there, or the examples over here. See the example over here. So what is a major factor to determine the size of your design? Okay, apparently the number of tracks will decide the size, will define how big your cell is. What do you mean by track? The parallel line segment, no matter what material you use, is called the track. The track, like the tracks are in the playground. Okay, the tracks, the runners are used. Track 1, track 2, track 3, track 4, and track 5. Okay, because we need spacings between every two tracks. So the more tracks you have, that means the more chip area you need. So if we reduce the number of checks in the implementation of a layout, then we are meant to reduce the area of that design. So how many checks we have in this one? 1, 2, 3, 4, 5, 5 checks in horizontal directions. And in the vertical direction, how many checks? 1, 2, 3, 4, 5, 6, 7. Simply counting on the number of checks, you can roughly, maybe very roughly, to estimate the size. Because a wiring check is a space required for a wire and the spacing from its neighbor. Okay, so basically, for example, in that way, okay, 4 lambda for the width, but you have to count the space between every checks. So the space and the check itself is called a pitch. It's called a pitch. It's called a pitch. That is a minimum space you need to use one check. Okay. So the more checks you have, the larger chip area you're gonna use it. All right. Transistor also counts on the wiring checks. So again, let me repeat again. No matter which material you use, the more checks you use, the larger area you're going to use it. All right. So that's the rule number 1. So you have to count the checks, or you have to reuse the checks. And the second thing is the well spacing. Because there is a requirement for the minimum space between 2 wells. Okay, this is N diffusion. This is N well. This is N diffusion. This is diffusion. So there is a minimum distance between these two. Again, there is a minimum distance between the well and its boundary. So the wells must be surrounded by the lambda, by the transistor, by equivalently about 6 lambda. So that means the more wells you use, the larger space you're going to waste. So don't ever do that. So preferably, if possible, we like to use one single well, N well, for all the P transistors. Don't use multiple N wells. Okay? A lot of students, they don't understand how to do it efficiently. I'll give you one example over here. See? Right now, if we need 3 PMOS transistors. Okay, this is 3 N wells, and then you like to have a PMOS here, PMOS here, PMOS here. A lot of crazy students do this kind of thing. Then, okay, logically speaking, or if this is violate the design rule, and it's not, because right now I use one small N well to carry out one P device individually. Okay, you can do it for fun. But the thing is, for reality is that you need a minimum space over here. That is large. You need this. So the better way to do that is you use a single but a little bit larger, okay, to include 3 PMOS transistors together in a single well. And this one is definitely smaller than the overall area that you cost. Okay, that is what I meant. Okay, if it is possible, please use one single N well to accommodate all of the P transistors. Okay, that will save you a lot of trouble. Not only save you a lot of trouble, that will save you a lot of areas. Okay, this is an important thing. All right, and this is what happened before. Before we go to the our workstation to do the layout, our TAs always ask us to do the estimation of what the area is. So this is the example that I just drew over there. We have to count how many checks. 1, 2, 3, 4, 5. 5 have horizontal checks. 1, 2, 3, 4, 5, 6, 7. 7 vertical checks. So before we go to the software, we can count the number of checks and find out what is the area that possibly you need to carry out this design. So unfortunately, the number is 40 by 32 lambda square. That is large. Okay, so, but however, for the beginners, okay, I don't blame you. All I ask from the students, beginners, is that make it work, okay? Make it work as long as the area you use is under the requirements of TSRI, that's fine, okay? Because it's free. But if your chip area is over the limitation set by TSRI, then your chip will be denied to be taped out, okay? That would be bad. You lose your opportunity to have your own chip without paying any money. And this is the real layout after you do the stick diagram. It looks almost the same as the stick diagram. It look like the one I draw over there. Okay, is it good design? No, it's not. Why is not? This one is easy to lay out, but if you consider the speed, this one is not a good one because as you see, we have a lot of space between these two transistors. We have a lot of space here. And that is why the previous one of the previous end design is much, much faster. This one. See, because this guy, okay, he or she deliberate, make it smaller until the limit of the minimum spacing. So the time for the current to travel from the left to right, or from right to left, will be shorter than the time of the other one. Okay, this is the other one. Because this one looks a little bit easier to be understood how you do the design. Okay, now I'll give you an example. What if this is the logic gate? Okay, if I ask you to lay out it, this is one. The square stands for the N. I cannot find the N symbol, that's why I use that one. So how do we carry out the design of this given Boolean equation? So I'm going to do it for you so that I understand how you do the design. So you are given a Boolean equation. That's a very simple gate. So this is y, okay, equal to A, B, C, and D. Okay, remember the procedures or the standard SOP that I told you before. When you got an equation, okay, don't panic. What you do? You reverse it. You reverse it. So you reverse it to find out what is like for the MOS device. When you reverse it, you're going to get this one. Okay? You get this one. This equation tells you a lot of stories. A lot of story. You see plus signs, that means they are parallel. You see N, you see they are in series. So basically, you understand that in your schematic, you're going to have 3 pair of transistor, then cascaded one transistor. So that's fine. So what we do it easily. So let's draw the over here. So there are a lot of ways to do that. So we know that we are going to have this one. Okay, we have 3 parallel transistors. Then we are going to have the last one to be in series with them. Okay, or they can be done the other way. We put 3 on the top. Okay? You can use this one or use this one. It's up to you. Okay? Is there any difference? The answer is yes. Logically, they are the same. Okay? But the thing is, when it comes to the performance, is there any difference? The answer is yes. Okay, we'll talk about it later, all right? The answer is yes. Okay, you might ask a question. How do we select, okay, which one is closer to the output and which one is closer to the ground? Okay? How do you select that? Have you learned how to do the selection when you took your microelectronics course? No? Yes or no? No, you were never been told, right? You were told that they are logically equivalent. The answer is yes, they are logically equivalent. But when it comes to the performance, okay, remember this one. We always like to make the fat guy close to the power supply or ground. Make the fat guy. Fat guy means that it has a bigger capacitance. So if you want to charge or discharge it, it will be faster. Let me repeat again. Logically, both of them are the same. Okay? But if we want to make the performance better, okay, we always have other options. Okay, other options. We can make the fat guy close to the ground or power supply because we want to discharge or charge it faster. Okay? That is why. All right? So this is number one. All right? And after we finish the design of MOS, then we are going to do the design for the PMOS. And as I say, they are dual. So on the top, you are going to have something like this one. They are in parallel, so on the top, you have 1, 2, 3 in series. And the last one is in parallel with them. They are in parallel. Those gates that they're in charge will be in serial on the top. Okay, they are in serial. The one that in charge will be in parallel. So no matter which one you select in the MOS, the upper parts, the MOS device must look like this way. Is that clear? All right? So, okay, let's see. Take a look. How does it look like? See? Before you go to the design, you see that? This is how it works. Okay? And how do we know which one to use? Okay? This is the one. So as I say, they select the fat guy because we have 3 transistors. Okay? And this, the capacitance over here is larger than this one. So as I say, we like to put the larger capacitor close to the power or ground. So they selected this one. Okay, so we remove this one, and this is the upper part, and this is the bottom part. So this is output Y. This is output Y. Okay, this is the one on the top, this is the one on the bottom. So right now we have 1, 2, 3. So how do we do that? Basically, we need a metal over here. Metal 1. Okay? And we have 1, 2, 3, 4. So we are going to have a piece of, I use a single stick. Okay? I don't want to do it very complicated. We have a piece of N diffusion. Okay, N diffusion. Right now, how many transistors we need? We need number 1, number 2, number 3, number 4. We have 4 transistors. And we like to what? We like to have these 3 transistors in parallel. In parallel, that means that either one have one end coupled to the metal 1, which is ground. The other one goes to the output. Then they're going to have this one over here, and this one goes to the output. And this one goes output, we have this one goes to the ground. All right? And then this one goes to the output. So we have to show them together. Show them together. Okay, show them together. And the output over, you see, this one, this transistor, one end it goes to the output, the other one goes, not the output, I'm sorry, goes to over here for the, to connect it to the last transistor. This is 1, 2, 3, and the output here goes to this one. And the last transistor here, one end goes to this 3, the other one goes to the output. Okay, that finishes this one. All right? For the topper part, I don't have a yellow, but I still use the, I don't realize, I gotta use the, over here. Then I have another metal. Metal one, this is VDD. Okay, and I have one end over here. This one goes to the power supply. Then I have 3 transistors in series. 1, 2, 3. This is 1, 2, 3. They are in series. And this one, the last one here, okay, they are in parallel. They're in parallel. So these are in series. One end is coupled to the VDD. The other one must go to what? To the output. Okay, the other one must go to output. And this one is this one. One end goes to the output. The other end got to go to the power supply. Okay, this one goes to output. This one goes to output. Then we show them together. Then it's done. And this is how it works. So you go from the equation, you reverse it, you develop the N block, then you use the duality to develop the P block, then you go to the stick diagram. If you don't like it, that's fine, just skip it, all right? Then you look at the schematic and make sure that both ends of a transistor is connected to the correct position. Then there's no trouble for you to finish the design. The only thing left right now is the size, WL. But right now, all the position they are all good. The last thing is that I forgot this one. Sorry, and you got to couple them together. And basically, when you can draw a stick diagram, then you have no problem to draw the layout. All you need is just expand the size. That's it, to the correct one. That's it. All right? So how many tracks we need? 1, 2, 3, 4, 5, 6. That's bad. Okay, that's bad. We need 6 tracks. 1, 2, 3, 4, 5, 6. 6 tracks. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 tracks in vertical directions. Okay, this is a stick diagram. And this gate is called the O3AI. Okay, OR3. We have 3 OR inputs and one, and then inverter. Okay, and this is how to do the layout. See, if you can draw the stick diagram, then all you need is follow your stick diagram, then expand it, enlarge it to the correct size. That's all. It's a size here, and the single strip to finish every design. And this one over there, look very like the one on the top. Okay, this is the layout. So see, as I said, if you can draw the stick diagram, you can draw the layout. Of course, let me repeat again. You don't have to go to the stick diagram. You can direct go to the layout if you have strong confidence and then you have enough practice, then you have no trouble. Because as I say, in my 30 years experience, okay, no students, none, zero, okay, show me that they want to do the stick diagram. They always directly go to this one. Okay, I think they are smarter than those students before. All right, I just let you know if you have a problem to develop the layout, perhaps you like to try the stick diagram first. Okay, this is the layout. Now we have more layout example in the future. Okay, this is the the layout, how to count the area, how many tracks? Six tracks. 1, 2, 3, 4, 5, 6. That's 6 tracks. And 5 tracks. 1, 2, 3, 4, 5, 6, 7, 8, 9. And they count only 5 tracks because they count each one metal. They count the metal. They count the metal. They count the metal. They count the metal. They count. The example in this figure that the author of this book only count the metal, okay, instead of count everything. If it was me, I will count everything into consideration. That will be 9 tracks, okay, vertical tracks. Okay, this is for the layout. We have more examples in the next lecture. Don't worry about it. Okay, and I think this is. Perhaps this is the maybe the last two slides of this talk. Okay, design views. I remember I talked about this before. Okay, there are a lot of views. So this kind of view it's not called the view. It's called the floor plan. Floor plan means that it's just like building a house. You cannot do it alone. You have to talk with your colleagues. You have to talk with your teammates. Okay, which block you are in charge. For example, this young man, he's asked by his teammates to do the design of a toilet, and the lady over there was asked to do the bathroom. Okay, and after you are asked, after you divided all the jobs equally between your teammates, and you start to work, okay, your own part. That's it. This is the design view. And there is a floor plan. And this is a software model, which we will not cover in this course because we don't have enough time. And the software model is widely used, okay, when you are going to do the system design. We have a course taught by other professors, which is called the HTL. Perhaps you'd like to take that one if you are interested. Then this is a view after you have your chip and you like to encapsulate it, okay? So I become a deep designer. And this is a view of a signal flow, okay? Which state is going to be moved to another one, and what kind of signal we are waiting for. And this is a transfer function. Remember this one. This is a transfer function, the input and the output. It is my belief you have seen this kind of figures a lot when you take other courses. And this is a block diagram view. And in the circuit design or system design, you like to see this one a lot because this is a tool for you to discuss with your teammates to clarify what you are supposed to do. And I think this is the last picture. Okay, FPL. We will not talk about this in the course, but I just let you know. It is called the field programming logic. Okay, it's not the cover in this course. It is not provided by UMC or TSMC. However, does this thing really exist? The answer is yes. I'll tell you why. Okay. A lot of chips, when they are delivered by the foundries, they are not really done yet. Okay, for example, the example I use is called the FPGA in your sophomore year, right? And there are other types of programming logic, which is called the ROM or POA, this kind of thing. Okay, this is a very special device. When you see this symbol, this is a very common one. This is a P transistor, N transistor, that's nothing. This is a transmission gate. You already know that. And this is a SRAM. But when you see a symbol, there is a small dashed line between the gate and the transistor. That means it has something special, which is called the floating gate. The floating gate, if you add very strong positive voltage, and they will attract a lot of electrons over here. Then suddenly you close, you cut off the positive strong signal. These electrons will be caught and trapped in the metal. Then what is going to be changed? The threshold voltage will be changed. Okay. The gate, okay, with lots of electrons, and those gates without electrons, the VTH will be different. And the difference of the VTH is going to stand for whether this bit is written with high or not. So that's why it is programmable. This is one special technology. We don't have it because it's highly confidential of the foundries. Okay, just to let you know what is one thing. And then if we can erase it, how do we erase it? We use a negative large voltage to kick out all of the electrons. Then the gate will be neutralized, okay, or restored back to where it was before. And the other one here is another special device. It is called the fuse. The fuse technology. Everybody has a fuse in their family. Okay, to protect overcurrent, kill your home appliance. Okay, if we have a small current, okay, it is a short circuit, that's fine. But if we want to program it forever, we simply send a big current to go through this small bridge called the fuse. Then it will be burned. Okay, then we don't have a short circuit. Instead, we have an open circuit permanently. Then it is programmed. So after it is burned, okay, there is no way to restore it. Okay, so that's why it's called the fuse. Just like the fuse in your house. If someday somehow you use too much power, okay, for example, you turn on every air conditioner in your house, it might cause a problem that you have the brake, okay? Then you go to the brake box to check whether the fuse is still there or not. Most likely, you're going to have a burned fuse over there. You got to replace it. I'll give you some numbers. For the usual house, okay, family living, okay, usually you have a 20 amps fuse, okay? And if you have air conditioner, you like to increase a little bit more higher. For example, you like to have one, just like that one, you might ask the electrician to increase the fuse to 50 amps because you like to turn on the air conditioning when the degree is over 35 or 38. You like to have a cooler room temperature, something like that. And this is a fuse. This is another type of fuse. It's the same. So after you burn it, it can never be recovered. Okay, this is fuse technology. So again, we are not covered. This will not be covered in this course. I just let you know, these are given in the textbook. Okay, we are going to more layout design. Okay, right now we only give you very simple example over there, just like the one. Simple gates, and or not, okay, NAND NOR, this kind of gate. Now what if we run into a lot of more complicated circuits? How do we do the layout? So lecture 6, is another core lectures of this course, how to do the layout efficiently. Physical layout designs and layout methods. Okay, so we are going to talk about a lot of things. How to do the layout efficiently, effectively, and can be easily reused. So what is the basic concept, or what are the basic concepts? And cell, what does this mean? Okay, the cell we talk about is not the biological cell that used in the College of Sciences. This is the cell that we use here, stands for a unit of design. And then we talk about the size, the geometry. Because up to now, we have not talked about anything about the size yet. Okay, we just tell you how to do the layout systematically so that you have a way to follow. And then we talk about the layout methods. Okay, these are the layout features, or let me refresh your memory. So N plus, called the N diffusion, okay, is the active area plus N select. And P plus, active plus P select. So that an N transistor is a poly over an N plus, like over here. Poly red over green diffusion, then it become N-type transistor, NMOS. And, okay, but on the other hand, by contrast, P diffusion and the poly, okay, and the poly will become a PMOS transistor in the layout. So these are the standard features for your layout. And there are some other tools to help you to do the layout. Because when you use the cadence of virtuoso, you will invoke a layout editor. Every layout editor, default, you will have a lot of dots. Okay, they are lined up in a square type. Don't erase them. Okay, because you need those grid, the small dots to tell you where you are and what the size are. Okay, what the size are. So that's important. The layout editors distinguish layers by colors, names, or field patterns. Okay, so you see different colors, okay, different names, and then you have different patterns. They could be this way, they could be the other way, okay, slanted. And all the design rules, they are God in the layout editor. You cannot violate it. Otherwise, your design will not be accepted, even though you finish it, all right? So what is inside is not important. Only the outline is important. The shape, the size, okay, is important. As those colors or the patterns or names, the purpose of these three features are only for the foundries to know what you need. Okay, so the shape and the size are critical. Okay, that information you have to give it to the foundry. Okay, what is a cell? Okay, in IC design, a cell basically is equivalent to the basic building block. So an AND gate is a cell, a NOT gate is a cell. Okay, all the gates can be considered as a cell. It can be as small as a single transistor FET. It could be as complicated as a logic gate. Okay, it depends on the way you prepare for it. But we have a definition for that. Each cell must have two types of ports: signal ports and supply ports. Signal stands for input and output and control, three types, in, out, control, all right? And the supply ports stands for two things, power and ground. That's all right? So understood? We need two types to build a healthy cell. All right, and before you go to the layout, you got to discuss with your friends, your colleagues, your classmates, how do we define these ports. Then after you define the ports, then you go to design, go to layout on your own. Why we have to define where the ports are, where the ports are? Because these cells will be and shall be, okay, used together directly. So this is the cell of an inverter. Then you got to discuss with your friends, okay, where the input port is, in the middle, in the upper part, or in the lower left corner, something like that. But usually we define this way, okay? The VSS stands for ground. They are sitting in the bottom. And the power supply port is sitting on the top. That stands for the port of the power supply. Then in the middle, okay, we have an input from the left, output to the right. Basically, we define this way. And perhaps you say, we are widows. We like to do it differently. That's fine. It's up to you. Okay? Because the bottom line is, you want your cells to be reused by your friends and by yourself in the future. So it's better for you to follow all the rules. And these are the symbols for the NAND gates. We have 2 inputs. If we have 3 inputs, you got to position those ports first. OR gates, then these are complicates, AND or inverter. Okay? And this is AND or inverter. Okay, you have to define where they are. Then you do the layout. Otherwise, your cell cannot be directly reused. And your friends will complain a lot. Okay, let's take a break here. I'll get a cup of coffee, and you take a break and go to the turtle room. And we'll be back after 5, maybe 10 minutes. Okay?